All right, we can probably think about getting started. So anyone who is able to, we'd love you to put up a cool structure as your background. Mine that I chose is called ePod. It's an art installation that I did the structural checks on to make sure all those people could be on the art sculpture and spin around in circles and not fall off and not hurt themselves. So structural engineering is very broad and you can do really cool things with it. Which leads us to the theme of this week, which is structural engineering. So Andy Vixman, one of the other mentors, and I will be talking about it in just a moment. In the meantime, if anyone who is having trouble using their cameras, if you can't get a background, that's fine. But if you are able to use your camera, we'd love to see your face. And if you're not able to use your camera, we'd really love if you could make your profile picture be something with your face in it, so that at least we can look at your face in some way. And I believe you can do this by going to your little thumbnail and right-clicking and then add profile picture. So you can put something on there that we can see you, would be awesome. Any questions about that? Okay, so we can get into it. How many of you watched the videos that we posted? I feel like I see less hands than last week. Oh, I see one there, Aiden, great. Lincoln, awesome. And so we did ask you to come up with one question or one comment from those videos. Does somebody have something they want to share?
I have a question. For like massive skyscrapers, like I have the Burj Khalifa in mind, how deep into the ground do those like footings go?
That's a really good question. The Burj Khalifa is actually especially interesting because Dubai is sand, and sand isn't that good for really tall buildings. So it's actually really loose soil underneath. So they had a lot of challenges building that building. For most, well, every building depends on where it's located. So a geotechnical engineer is another engineering profession, and they go and do a site analysis to determine what kind of soils are under your site. And so for some smaller buildings or semi-tall buildings on really good soil, your foundations might only go a couple feet into the ground. But then for a really tall building like the Burj Khalifa, you want to go super deep, maybe even hundreds of feet, or down to a good layer of soil.
Okay, thank you.
How about some more comments or questions? Anybody else? All right, we have a question from Ivan. So let's say a society hires a team of engineers and architects for a building, and after construction, it collapses. Who is going to be responsible for the loss, the engineers or the society, considering that the society gave strict criteria and constraints to the project? Does another mentor want to answer that?
So I practice forensic engineering, and a huge part of my job is coming in after the fact and looking at those things of who knew what and when and where and who met what's referred to as their standard of care, which is generally, did they act the way another engineer, another architect, or another owner would act in the same position? And the short answer is it depends on the contract and code requirements and all the different things that apply. You bring up a good point. If the engineer designs something made of steel and the owner comes back and says, I'm only paying for balsa wood, you're going to have a problem. But an engineer has a stamp and puts a stamp on those documents saying, this is what I agree with, this is what I say will work and will be built. and if it's built, and they're saying that that will work. A lot of times what we see though is that there's differences between what's on paper and what's built. And so that again gets very complicated. So there's a whole industry of us who look through those things and trying to figure out what and why and how do we move forward? How do you fix it?
Thanks, Liberty. And Anna looked up exactly for the Burj Khalifa, and it goes 164 feet into the ground. So pretty deep. Any other questions or comments before we launch into things? I see a lot of really cool backgrounds, so thanks for sharing those, everyone. But we can get started on structural engineering. So let me share my screen. There we go. All right, so as I mentioned, we're going to be talking about structural engineering. You hopefully watched some of those videos, so you'll have a kind of a sense of what's going on. We'll just give a brief, quick overview of some of the stuff that wasn't covered. And if I can advance. All right, so my story is I went to Boulder High, go Panthers, and that's why I'm connected to you all in Colorado, even though I finally made it back to New Zealand. So I'm talking to you from a quarantine hotel in New Zealand, which is pretty cool. But anyway, after Boulder High, I went to Cal Poly San Luis Obispo and studied architectural engineering. It's a great program. It's really specific to structural engineering. So there's other architectural engineering programs like at CU, and they focus a lot on the MEP side of architectural engineering. But at Cal Poly, we did structures, which was great. And then I afterwards felt like I wanted to know more about earthquakes. So I went to the ROSE program in Italy, and I studied for my master's in earthquake engineering. And then afterwards, I ended up with a company called Home Structures in San Francisco and New Zealand.
And then I'm Andy. I went to Cherry Creek High School. After that, I did a program called Engineering Plus at CU Boulder. It's a pretty new program there that's really cool. I did engineering while also getting an education degree. So I studied civil engineering there and focused on structures, but also did some education stuff and ended up teaching high school for a year. Then I ended up going to Purdue in Indiana for grad school and studied structural engineering there. The picture there is a picture of the really big structures lab that I'll be talking about later, where they do lots of full-scale testing of different pieces of structure, which is really cool. And after that, I now work for Martin & Martin Consulting Engineers in Lakewood.
And just to cover, we've been covering a lot of different disciplines, but we haven't gone through as much to say how everything relates to each other. So this is a good graphic to kind of show you that. And maybe Andy, you can elaborate on it.
You should elaborate on this one. I'll do the next one.
So there's usually an owner who's either an owner or a developer. They have the site and they want to make it into something. So Joey talked during the architecture session about how there's multiple ways that you can go about hiring the different disciplines. So there's something called design build, there's something called design bid build. And if you want more clarification on that, then refer back to the first session that we did. But once that's sorted out, you have two major teams. One is the design team, which has the architects, all the engineers, the interior designer, landscape architect, urban planner, who are creating the plans and the designs for what the building's going to look like. And then you have the construction team, who's the one actually going to site and creating the final product. So any questions about that or any of the particular roles? All All right. Well, keep these things in mind because you'll need to know them later on today and in the future.
Sorry, I had a question.
Yep.
The steel fabricator, like I know there are all these new like fabrication labs. How did, maybe this is a bad question. How was steel like shaped how people wanted it before all those labs were a thing?
That's a good question. I'm not sure what you're talking about in terms of being a new thing. Steel fabrication has been around for quite some time. And in the lab, they have a big melting pot and they put all the steel and all of the different ingredients in to melt it down into a liquid. And then it comes through an extruder and it gets extruded into the shapes that we make and use. So the steel fabrication has to do with the making of the steel shapes, but then also if for a certain project you need things welded or you need them cut to a certain length, then the steel fabricator also goes in and does those things too.
Okay, so it has been around for a long time. Fabrication, not just welding. All right, thank you.
All right. So just to clarify the difference between architecture and engineering, what we've been doing so far has been more architecture focused. Obviously, last week we got into civil engineering and we started looking at some of the utilities coming into the site. But when you're talking about the building itself, engineering and architecture are different. So the graphic I'm showing here is kind of something that you would focus on more as an architect. You do the site analysis, the site plan, all of that. And as an engineer, I get kind of bored with that stuff. That's not where my passion lies. What I really want to do is I want to find X. You know, I'm more of the math-minded person. I want a final answer. I want to say this works or this doesn't work. It's a little bit less artsy, but it is still a design professional. So you're still going out there and doing a design to create the final project that is the building. And to further explain that, when you look at most buildings, they are these finished architectural products, right? They look like the architect wanted it to. So where is the structure? It's the bones of the building. It's the beams, the columns, the floors. That's what we as structural engineers design so that the architectural form can stand up and not collapse, right? We don't want that happening. So I call it the bones of the building is what the structural engineering is. And there's a lot of different materials that you can use to get that finished product. Here are two examples of tiny homes. So can someone tell me what the material on the left is?
Mostly wood.
Yeah, it's called wood or timber. And so those are timber studs that are built using to build that tiny home. And how about anybody for the one on the right?
Metal.
Yeah, it is a kind of metal. Anyone know what specific type of metal?
Steel.
It is steel, not aluminum. But aluminum does look similar. So it is called light gauge steel. Gauge is referring to the thickness. So it's a really, really thin steel. You could think of it kind of like tinfoil, although it is thicker than tinfoil. And they make these steel studs, is what they're called also, that you can use to replace wood. And there's some benefits to that, like termites don't get into it. So those are two good materials for building tiny homes with. And some other materials are here. So what about the one on the left?
Heavy gauge steel.
Yeah, we just call this one normal steel. Perfect. And what about the one on the right?
Concrete?
Yeah, and there's all these things sticking out of the concrete. What are those?
Copper barbs or metal barbs?
Are those steel?
Rebar.
Rebar.
Yeah, it's rebar, exactly. So rebar is made out of steel and it's usually has these grooves on it so that when you pour the concrete into the form, you get a bond between the steel and the concrete. And the form is the usually wood casing that they pour the concrete into. So this column is hard now, but when it was wet, because concrete's kind of a liquid when it's first mixed, it's like this slurry liquid that they pour into a wood formwork, which would wrap around in the shape of this column. And then once it's hard enough and solid enough, they can remove that and you get your finished form. All right, the last two materials we're going to talk about. So the one on the left, anyone?
Brick or masonry?
Yeah, brick masonry, perfect. And that one's used often more as a decorative feature because it's not that great structurally. The steel that we use in concrete is so that we can pull on the material. So tension is a pulling force, and concrete itself is really good when you push on it in compression, but it's not that great when you pull on it. So the steel is there to allow you to have that tension force going through the material. But brick is a lot like concrete and it doesn't have that tensile capacity. So if you can add steel to it, you make it better. But we usually, if we are building with masonry, we build with the stuff on the right, which is called concrete masonry unit. And there's gaps in between those gaps in those units that you can fill with steel and grout to make it stronger. And here's another example of a tiny home. This was one that my company designed. And so you can see it's light gauge steel studs that they're using, but then over here, there's a cantilever. And a cantilever is when you have one side that's fixed and one side that's bouncing around. So the connection back here at the fixed end is really important so it doesn't just collapse or move too much, make it too bouncy. That's really important to think about when you're doing cantilevers. And so the light gauge steel wasn't strong enough in this case, so they used heavy gauge steel to frame out this cantilever to make it stiff enough so it wasn't bouncy.
Perfect. So some of these words on this page, Nicole already said, she talked about compression and tension when she was talking about concrete. So that's like compression is like a pushing force, tension's a pulling force, but there's also lots of other forces that we have to design for as structural engineers. There's bending, there's torsion, there's shear, and all of these different things are things that we're considering when we're coming up with a structural system for a building to make those bones work and make the building stand up. So something we talk about a lot as structural engineers are loads. Does anybody have any guesses as to what type of loads might act on a building or structure that an engineer would have to design for? What kind of things do you think we have?
Well, there's people and furnitures.
Perfect. Yep, people and furniture, that's a great one. That's what we as structural engineers called live load, because your people or your furniture are not always in the exact same place, right? So we call it a live load because it could potentially move around. So we design based on that. What else? Thanks, Kate. That was a good one.
There's also dead loads.
Who said that? Sorry, I can't tell. Dead load.
I said dead loads, and Enrique said something else.
Yeah, Enrique, I'll get to you in 1 second. Aiden said dead loads. Perfect. Aiden, what do you mean by dead loads?
The weight of the building itself, and yeah.
Yeah, Aiden's in a civil engineering class right now, so that helps. But exactly, that's what we call them, dead loads. It's the actual weight of the structure. So your concrete beam or your steel piece, whatever Nicole was just showing us, all the structural elements, that's the dead load we also have to think about. What else? Enrique, was that what you were going to say, or did you have a different idea?
No, I also had like the factors of the wind or the ground shifting, like maybe if you're in California on that line.
Yep. So those are actually, you got even further. So the loads that we've been talking about so far, like dead load, live load, are all what we call gravity loads or vertical loads, because those all act down on your structure, right? People are acting as a load down on your structure. If you've ever taken physics or drawn a free body diagram, that's like our downward loads. gravity loads. Enrique is talking about what we as structural engineers call lateral loads that act sideways on the building. So wind is definitely a really good example of a lateral load. Earthquake loads are also lateral loads because they shake the ground and cause buildings to have loads going sideways into them. So those are other great examples. What other natural elements could you think of that might cause load to a building besides wind and earthquake?
If
Snow
the
loads.
building floods.
Floods
Go
and
ahead,
snow.
Lincoln.
I heard Lincoln
Yeah.
say snow and Aiden say floods, rain. Those are two things that are really important. So like if you're designing for a building in Denver versus if you're designing for a building in the mountains, you have a completely different snow load that you consider because they get a lot more snow in the mountains. So there's a lot more load that could potentially be stacking up on a roof or something like that. So I think we hit most of the ones that I want to talk about. That's a really good summary of all of the different types of loads that we look at. And then this picture shows that those loads, typically, if you have like a regular structure, go into your floor, which we call a slab typically. And then from there, go into your beams and into your columns, and then into your footings or your foundation elements. So something that's really interesting as structural engineers, we actually usually start at the top of a building when we're designing and work our way down because your loads all end up traveling down into your foundations. But when they build buildings, they obviously start from the bottom up. They can't start really with the roof. They're going to start with what's going into the ground. So we have a little bit of a timeline issue sometimes in that they want us to have the foundations done first so that they can start building them. But we have to know everything that's happening above the foundations to design the foundations. So that's just something interesting that we deal with as structural engineers. I think the next, is there anything else I missed on that, Nicole? Are we ready for the next one? Okay, so this is just funny. I love Despicable Me, and Nicole does too. She included this. So our job is to make things stable, make those bones work, and make sure that things aren't falling down, and we don't want all of the disasters that happen. So did you just fall? No, I attacked the floor. We don't want anything falling. We want to make sure that everything's stable. Next slide. So this is actually what Enrique was talking about a little bit with his earthquake and wind loads. Those are called lateral forces, like I talked about. So they go sideways along your building. So we talked about like the beams, the columns, the floors, the foundations. Those all are called gravity elements, really. They take vertical load. When we have something acting laterally, we typically have to deal with that through our walls. So we can have shear walls, we can brace our building with diagonal braces. There's a bunch of different ways that we deal with that, but we actually have two separate systems. We have a gravity system to deal with all those loads and a lateral system to deal with sideways loads. And then something that is true of all of the different pieces and people that work in the ACE field that Nicole was talking about at the beginning that we haven't necessarily talked about is we all have to document what we want the building to look like and all the different pieces. So this also comes back to whose fault is it if something bad happens. You have to have your documentation that shows what you wanted, what you intended with your design. So Nicole's picture here is part of a Revit model, which is what a lot of us use these days. It's a software that we use that we can design our buildings in and actually model all of our pieces of our building. So the first picture on the top left, it just shows what a structural model would look like, where we actually model in our beams and our columns and our foundation elements and our floors into Revit. The picture right next to it is like an analytical model where it can design some stuff. But then when we actually want to give drawings to the people who are building our buildings, to the architects when we're coordinating all of these different things, we have a bunch of different things that we include in there. So the picture on the bottom left that Nicole is showing is called a plan. And that's what your building looks like when you look straight down from the top of it. It's like a bird's eye view. And so that's one level. We usually have a plan for each level. Sometimes we'll have, our building is so big that we want to show pieces of our plan. So we'll have multiple plans per level, but you pretty much have a plan per level. Then we also have on the right, those are sections. So those are where you like cut through the building and are looking through a specific part at a section to look at something more detailed. So those are a bunch of different things that we include. We also include elevations, and Nicole included this really cool elevation of a project she's going to talk about. But that's what it sounds like. It's looking at the side of your building and what that would look like. And you can include those to show those elements as well and show different pieces than what you would see looking down on your plan. And we include all of these drawings in our set, and that's what we give to the steel fabricator and the construction manager and all of these people so that they know what actually needs to happen in the building. And another piece of this is obviously our buildings are not paper sized. So when we print them out on a piece of paper, that's not the size of the actual building. We have to scale things down. So Nicole and I thought this picture on the left was pretty funny in that your car might be one size, but what you actually print is a different size. So we have architectural and engineering scales, which some of you might have used before in ACE. Since we're not in person, obviously we don't have the whole scaling activity is easy. So we just wanted to talk about scale and how that works. So if our building is actually like 40 to 80 feet long, let's say it's a small building, we have to scale it down, and we have a specific scale that we use on paper so that if you measured out 1 inch on paper, it would equal 3 feet in real life, or depending on what your scale is. So 1 inch is 1 foot, 3/4 of an inch is 1 foot, and we all use that scale so that we know what size our actual building should be. And that's anything else we need to say about scale, Nicole?
No, I think you did it well. Anybody have a question about scale? Does it kind of make sense?
Or anything else we've talked about yet? Any questions? Yeah. This is a good place to pause for questions. If you have questions on scale, now is a good time to ask them, because we are going to be somewhat quizzing you later with a Jeopardy game, and there are lots of scale questions in there.
How can you, like, I know it's in the bottom of the corner on the plans, but for the ruler, how can you tell like which one's where, if that makes sense?
Yeah, I think I get it. If I don't answer your question, let me know and I'll try again. But so for the rulers that are here, it typically will like show the scale on the ruler. So you can see, I'm not as familiar with the architectural rulers, but the engineering scale, like the bottom one looks like 1 inch is 30 feet is the bottom one based on the 30 there. The middle one's 1 inch equals 20 feet, and the top one's 1 inch equals 10 feet. And that helps you see that there. Was that your question with the rulers? Okay, and then it will say that scale on plan like Enrique talked about, and that helps you know, or on your drawings, what scale it's actually to. Any other questions?
I got a question. Why would you use a architectural scale over an engineering scale, or vice versa?
That's a great question that I do not know the answer to. Nicole, do you have a good answer for that one?
Honestly, I don't know how to use an engineering scale, and I am an engineer. We always use architectural scales because we're making our plans look just like the architectural plans. So usually the architect will choose what scale. Let's say they're doing 1/8 of an inch equals 1 foot. So then our plans would be that same size, so that when the contractor is going to build it, he can look at 2 pieces of paper and see the architecture plan and the structural plan and say, okay, this is there, so that means this is there on this plan, and kind of match things.
I can weigh in, Nicole, on that question for Ernest. The engineering scale, if you look at the scale down at the bottom, it's a lot larger scale. So if you think of a site plan, you know, you have a 1 to 50 inch scale. That doesn't, it's just a larger scale. So you have to have a smaller increment to measure by. Whereas the architectural scale is like an 1/8 inch equals a foot, a lot larger scale that they need to use versus a smaller scale for a civil engineering project or such. And there are times when we'll use, for like a site plan, we'll use an engineering scale for the site plan on an architectural drawing because we need to get it to that. We need to fit it on a sheet at that scale. So it's really a site scale versus a building scale.
Thanks for that. Any other questions? Feel free to interrupt us at any time if you have questions as they come up. I think we're good with that, Nicole, if you want to talk about the next slide. Oh, wait, I'm still talking. Okay, so these are some videos. So one of the things that we do as structural engineers, like Nicole and I design buildings, but there's lots of different pieces. So Liberty was talking at the beginning about forensic engineering, where she goes in and tries to see what happened when something goes wrong. Another part of engineering for structural engineers is actually research and trying to make things better. So this is the lab at Purdue, which, like I said, is a full-scale lab. So this is a 20-foot-long beam that my friend built. You could actually see him in that video pushing on something. He's actually putting load into this beam. So it's being loaded at 2 different areas, and the program is quitting, but that's okay. It's being loaded on the left and the right, and he is testing this rebar in the beam. This is called 100 grade rebar. So it's a little bit stronger than what we typically use right now. So typically we'll use 60 grade rebar. And so he's testing how long the overlap needs to be between those 100 grade rebar in the middle. So when you have a beam that's really long, you can't fit one piece of rebar all the way through it. So you have to have multiple pieces and you overlap them a certain amount. And so he was testing how long did that overlap needed to be? Did it need to be longer or shorter? So that was his beams that he was testing. There's lots of different things that get tested in research labs all over. Purdue has a really big lab, so they test really big things. Like someone else I knew built a 30-foot tall wall, and then he built it flat and then stood it up in the lab and tested that. And he was testing that for earthquake loads. Lots of different things that happen. So that's just some cool videos and cool things in structural engineering. We'll see if it quits again, but there's some cool videos of his explosive tests. The first one he did, he actually was not fully prepared, and a piece of concrete shot up and hit his laptop and broke his laptop. So then they put the screen up after that, which was way better. This is another one that he broke. We'll see if this video works. The first one I took, and I definitely jumped every time because it's loud. So I jumped in the last video. I think someone else took this one.
Oh man.
It froze. Oh well, we got to see one.
Sorry. Yeah, you saw the breaking one at the beginning. So then we'll switch gears to analysis models. We don't always have the luxury of building something in a lab and breaking it. That's kind of the research side of structural engineering. As a day-to-day practicing professional, we want to make sure something works and test it, but we do so by making a 3D model. So this is an example of a 3D model that we ran an earthquake record through. And so this is basically seeing how the earthquake would shake the building and see what would fail and what would be okay and where we need to add more strength or stiffness. Stiffness is basically how flexible something is. So that's what that was. Let's see if I can get PowerPoint back open. In the meantime, any questions? Oh man.
So how would the models know how the building would react to like certain earthquakes or the load of each materials? And how would you use like different materials in a building if like it's like that model and it all looks the same?
Great question. Andy, do you want to answer?
Sure. So like Nicole was talking about, stiffness is really important in that. So it actually knows when you build a model how stiff that element is based on, you tell it like I'm using this size beam, or I'm using steel here, or I'm using concrete here. So our modeling programs know that, and then they distribute load. Load goes where things are stiffer. So it distributes based on that. There's also, it's a pretty complicated analysis program typically that runs through and does like, it's called finite element analysis, which is something that you don't learn about till way later in school, but it looks at little pieces at a time and sees how each little piece is working, and then combines that to look at the whole beam or the whole column, and then eventually the whole building to see how it reacts.
Yeah, and the programs are set up to do calculations based on the building code. So the building code is a document that's put out by various agencies that tell us legally the minimum requirements for how to design something. So it's meant to be the practitioner's best understanding of how to do a design to make it safe for everyone, with some factors of safety in there to make sure nothing goes wrong. And so these softwares are set up to do those checks for you. All right, so as I just said, we want things to be safe. We want to have extra factors of safety in our design because we don't want things like what we're showing here to happen. You don't want, this building was torn off its foundations from a hurricane. So it just got lifted up and pushed over and totally collapsed. And then this building on the right is from the earthquake in Nepal a couple of years ago. And these are buildings made out of unreinforced masonry. So unreinforced means no steel rebar. And as I said, that's not a very good material, especially not in earthquakes. And it's really heavy, so it can fall and hit someone on the head, which is not good at all. So we want to avoid this when we're doing design. And in conclusion, engineers aren't boring people. They just get excited over boring things. But I don't think so. I think you can do a lot of really cool things with engineering, like my background here. It's a really cool art exhibit. And another cool project I've done is a zipline roller coaster. Now, the one on the left, I'm not exactly sure where that one is, but the one on the right is a 3D model of the zipline roller coaster I helped design in Tennessee, in Pigeon Forge. So if you're ever there and you want to go ziplining, it's really cool. We have rigid rails, so you're able to make turns, like you get to loop around a tower and make a turn here. So it's really awesome what you can do with structural engineering. More towards the home side of things, this is a house in San Francisco that someone had the idea of blasting out this whole back wall and turning it into a swimming pool down here. There's a basketball court here, a yoga studio up here. So there's some really interesting designs and buildings that you can do with structural engineering also. And the elevation we were looking at before was this zipline roller coaster. So engineering saves lives. We're doing that every day by making buildings safe so that all of us can walk into something confidently and not have to worry about the floor collapsing under our feet, or if there's an earthquake, we feel like it's going to protect us and not just crumble on top of us. So it really is about saving lives. Any questions?
I have a question.
Mhm.
I was born in Kansas, so there were a lot of tornadoes growing up. And I just want to ask, because I know my house had a basement. I remember like whenever it was tornado season and people were expecting tornadoes, my mom's friends and other family members who had houses that didn't have basements would come to our house to stay in our basement whenever they thought the tornado would come. So I just want to ask, is there like any extra consideration where like when you're building houses specifically on tornado valleys to make sure that they're strong enough to withstand or tornado where they don't have any other kind of protection throughout the house?
Yes, there is. One of the people that I work with actually worked in Oklahoma before he came back to Colorado, and they have lots of tornadoes. And so there's a whole separate, that's a different type of load that you design for, like an earthquake you would design for tornadoes. And houses, there's pieces that go into it. Another thing that we didn't talk about, but depending on the purpose of your building, you can design for different types of loads. Like a hospital has to withstand more than a house, or a school has to withstand more. So different types of structures are designed for different types of load. And so a tornado hitting a hospital, when you design that hospital, you really make sure that it would be okay during a tornado, things like that. But houses, yes, are also designed specifically for that in those areas.
And one interesting fact, I'll say it as a public service announcement, is that when we're designing, especially for earthquakes, we don't design for the building to be totally perfect after the earthquake is over. We design buildings to protect people. That's our ultimate goal, is life safety is what it's called. So we want people to be able to get out of a building safely, and the building might suffer because of that. So there's a field that it's called performance-based design, which then you can say, I want my building to be 100% perfect after an earthquake or some tornado or something like that. And you can design a stronger, better building because of that. But the basic building is just going to protect you and not necessarily protect the building.
There are similar sub-industries that work specifically with blast and explosion considerations for that same, usually governmental buildings, but that same extra consideration of potential forces that most buildings we don't expect to see.
I'm loving all the questions today. Thank you,
Yeah.
everyone. Keep it coming.
Nicole, you said you really like finding the answer and like finding the X. My question is like when taking into account all the loads and the physics, like what needs to be processed to confirm that structural ability, or does it need to be able to support more weight than what you're anticipating or hit zero, or probably not? How would you?
Yeah, great question. So we talked about all the different types of loads. And when we're assuming what our load's going to be, we want to have some extra just in case in there so that we're designing something not right to the limit. Because if you design right to the limit, you don't know how it's going to perform in the real world, but you also don't know what if the architect changes the layout and suddenly your beam has to get 2 feet longer? Is your beam still going to be okay? So we want to design with some factors of safety, like I've been saying, in there. But basically, you take the loads, you see how much load is going to an element, and you design that element to be stronger than that demand.
Got it. Okay, thank you.
All right, feel free to keep asking questions. We are gonna shift to something more fun and interactive. So we're gonna play Jeopardy! And I don't want the same people answering every time. We would like a variety of people to answer and pick questions. If you pick, you don't have to answer. Anyone can answer. So don't feel the pressure to say, oh, 400 for design professional, and then not know the answer. Somebody else can chime in. So we'll just play all as one team, but who wants to choose a category first? Enrique, go ahead.
Construction team rules for 500.
All right, so who cuts, bends, assembles, and welds steel?
Is it the steel fabricator?
Awesome, you got it. Oh, how do I do this? There we go, yay.
You have to hit the spacebar, then escape.
Yeah, I don't think it tells us if we got it right, but you guys got that right. So next category.
Oh, do I choose because I got it right? Okay.
There's 400 for construction rules in the chat as well.
Yeah, we'll do that one, and then Aiden, you choose the next one. Checks that property lines at the site are correct and notes special features of the land like slopes or wet spots. This one's kind of tricky.
What's a environmentalist?
Good guess, but not correct in this one. And an environmental engineer is often concerned about the quality of the soil. So if there's something poisonous leaching into the ground or whatnot, they would be concerned about that. This is a little bit more specific to construction and the person mapping out the changes in the slope on the site and whatnot.
Is it a surveyor or something like that?
Awesome, Kate, you got it. So far, 100%. Great. And then we were gonna choose Aiden. Did you want to choose one? Aiden Smith.
Okay, let's do design professional roles 100.
Designs the skyscraper, determining its height and shape, choosing its style, and selecting the building materials to fulfill her creative vision of the building, her or his.
What's an architect?
Awesome, Enrique. All right, next one.
Let's go scale 200.
Practicing scale.
Sure, yeah.
If the scale of a drawing of a door is 1 inch per 2 feet and the door is 8 feet long, how many inches will the drawing be?
4 inches.
Great. Good job, Kate. Everybody understand that, or anybody have a question about that relationship? Okay. How about someone who hasn't chimed in yet? Give me a number.
Let's do to scale or not to scale for 300.
Okay, so this is basically asking, if you outline your hand on a piece of paper, are you drawing something to scale or is it not to scale?
To scale.
And by to scale or not to scale, because this confused Nicole and I, are you
Yeah.
scaling it up or down, or is it an accurate representation?
An accurate representation.
Yeah, so we
Right.
consider that like not to scale. Nicole and I both got really
Oh.
confused when we looked at this one.
Yep, so that one's the normal size. That's 1:1. So it's not to scale. Great.
Wait,
let's-
sorry, will you explain that really quick? Because
Yeah,
it
let's-
sounds like it would be to scale since you're measuring your the actual size.
So scale is when you're making something bigger or smaller than it is
Oh.
in reality. Not to scale is saying it's what is reality.
The terminology is confusing though. As long as you understand what we do when we scale things, we're good. But that's what this category is saying specifically.
Yep. Let's do another one to see if we understand. So drawing an accurate picture of the Brooklyn Bridge on graph paper, is that something to scale or not to scale?
Would it be to scale?
Correct.
Oh.
Yep, because you can't draw the whole Brooklyn Bridge on a piece of paper. That's this huge, ginormous thing. So you have to scale it down so you can actually draw it. I think Emery was going to choose a category.
Let's do design professional roles 200.
Cool. Develops land use plans and programs that help create communities, accommodate population growth, and revitalize physical facilities in towns, cities, counties, and metropolitan areas.
Is that an urban planner?
Fantastic, it is. Another number.
Construction team rows 200.
Renovate and re-lease existing buildings or purchase raw land to later build on and sell.
So who actually buys the land that we do all of this stuff on?
What is a contractor?
They're the ones who build it. So who
Is it a
owns it,
developer?
who buys it? Yeah. So developer or owner. Awesome. Let's do maybe 2 more, unless you all want to keep going. How about someone who hasn't spoken yet? Just throw out a number. You don't have to answer it if you don't know.
Design professional roles 300.
Great. Designs all aspects of the natural environment.
What is the landscaper?
Landscape architect. Yeah. Lincoln, do you want to give us one?
Sure. What is practicing scale practicing scale 500?
Oh, going big. If the model is 20 inches and the actual object is 100 feet, what is the scale?
1 inch to 5 feet.
Awesome. You're quick at math, Kate. Nice to be done. So basically what she did was take 100 feet and divide by 20 so that it becomes 1 inch. And then that ratio is 5 feet. Let's do one more scale just for good measure, and then we can go into our breakout rooms. So if the scale of a model of a building is 1 inch per 4 feet, and the model of the building is 8 inches long, how many feet is the actual building?
What is 36 inches? Or 32?
Close
Or
enough.
feet, yeah.
Great job. Awesome, everyone. That was super fun. I hope you enjoyed it as much as we did. And let me check the agenda. Joey, is there anything else we need to cover before we do breakout rooms?
No, nothing that I can think of other than if anyone knows the building that's currently behind me from watching the videos that they were supposed to watch. Any
I don't
idea?
know the name, but I know the pillars were like more
Honestly,
centered,
no.
so that did not help.
That's the
the
building
wind.
that they did in secret.
Yeah, this is one of my favorite lessons from architecture school. I can share a link to an article later of Citicorps Center, but a grad student in structural engineering actually was the one that found the mistake as they were nearing the end of construction. So they went in at night in New York to beef up the structure and make sure it didn't fall over, but it could have been very catastrophic. So it was an almost failure. Good job, guys.
All right, and I just sent around the link for SketchUp. If you could open that, we will be doing an activity in the breakout rooms with SketchUp. And hopefully some of you watch the video so you kind of know what's going on. Other general announcements, we really would like you to fill out that survey that Joey posted. And when you fill that survey out, we'll be able to know what things that we need to send you, because we will be sending some of the base maps printed to scale and everything that you'll be able to use. So there is a result that comes from this survey. Answer as many of the questions as you feel like it, but we do need just the basic information from that survey completed. So please, please fill that out ASAP. And the other announcements is we're going to do SketchUp, and then please, we're going to do a quick break while we transition you into the breakout rooms. You'll have 5 minutes. So let's say until 5 o'clock, and then come back here. And in that short break, we are going to ask you to go get as much toilet paper as you think you need. So grab some sheets of toilet paper, however many squares you want to, and come back to the breakout room with that, please.
Take that time to get up and stretch and move around a little bit, since we sit a lot during these meetings. So it's good to get up and move around. And that was a suggestion on my questionnaire that I really appreciate. So I won't call that person out, but thank you for putting that suggestion in.
Yep, so go get some toilet paper. We'll put you into the breakout rooms now. Very cool.